Hello everybody, welcome to this short collection of examples. So today the examples are based basically on the first three questions in the calculus part of the second homework sheet. So the three integration problems, and in each case we have to figure out which of our techniques of integration might apply. So the first one's here, it's integrate from 0 to the square root of 3, this expression r over square root of 1 plus r squared. And here, it's not an obvious candidate for integration by parts, and it's certainly not a candidate for a partial fraction expansion because the denominator is not a polynomial, it's a square root. So what remains to us is a possible substitution. And so to consider that, we should ask ourselves, is there some component of our problem whose derivative also appears in our problem? And we might notice that the denominator there has a 1 plus r squared in it, and the derivative of that is 2r, which resembles the numerator. So we could try substitution, u equals 1 plus r squared. Okay, if we do that, we get the du dr. We want to translate our problem into u is 2r, which says that du is 2r dr, and that we can rewrite this part r by dr as 1/2 du. Okay, so the r dr gets absorbed into 1/2 du. The limits of integration when we are at r equals 0, which is the lower limit, then u is 1 plus 0 squared, which is 1. And when r equals the square root of 3, which is the upper limit, then u equals 1 plus the square root of 3 squared, which is 1 plus 3, which is 4. So our integration problem, when we translate it into u, becomes, well, the r by dr becomes 1/2 du. So we pick up a 1/2. The 1 over square root of 1 plus r squared is 1 over the square root of u. And we're integrating from u equals 1 to u equals 4. So this is 1/2 integral from 1 to 4, u to the power minus 1/2 du. This is at this stage a relatively straightforward problem. It's the power of u. And to integrate u to the power 1/2, we increase the power by 1 from minus 1/2 to plus 1/2, and we divide by the increased power. Sorry, that's a plus 1/2. We've increased it by 1. So get u to the 1/2 divided by 1/2, which means multiplied by 2. And that's evaluated between u equals 1 and u equals 4. The 2's here cancel each other, and we're left with the square root of u. And u equals 4 and u equals 1, which is the square root of 4 minus the square root of 1, which is 2 minus 1, so that's equal to 1. Okay, which again means the area of the region enclosed under the graph of that function between 0 and the square root of 3 is exactly 1. Okay, our second problem, which resembles somewhat the problems in the second calculus question of the current homework sheet, is an integral of x times e to the 2x. Okay, and now this is kind of classic integration by parts example where you've got x multiplied by some function that we can write down an antiderivative for. Okay, it's not a substitution example really because there's no clear choice for a substitution. So, but this is a candidate for sure for integration by parts. Remember how that works. We have in our integration problem a product. We're going to call one factor in the product u, and we're going to choose u if possible to be something that sort of gets better when we differentiate it. So if we take u to be x, then u dash is 1. If we take v to be e to the 2x, sorry, v dash to be e to the 2x, then v should be an antiderivative for that, which is not really any worse than e to the 2x itself. So we want to find something whose derivative is e to the 2x. We should basically take e to the 2x. That's not quite right because it's out by a factor of 2. The derivative of e to the 2x is 2 times e to the 2x. So to compensate for that, we should take 1/2. So our v, our antiderivative for v dash there would be 1/2 e to the 2x. Then the integration by parts formula will tell us that the integral of uv dash should be uv minus integral of u dash v. So our integral from 0 to 1 of x e to the 2x dx should be uv, which is 1/2 x e to the 2x from 0 to 1, minus integral of u dash v, which is minus u dash is 1, v is 1/2 e to the 2x, so this is minus the integral from 0 to 1 of e to the 2x. So we still have something to do, but we have replaced our original problem with the problem of just integrating e to the 2x itself, which is certainly not as bad. Okay, so just writing down the details here. This is 1/2 x e to the 2x, evaluated at x equals 0 and x equals 1. And then we've got minus 1/2, and we've got to take an antiderivative for e to the 2x. So again, first guess is e to the 2x. That's too big by a factor of 2. So we should divide it by 1/2. And we have to evaluate that between 0 and 1. Okay, so finally, putting x equals 1 here in the first term, we get 1/2 times 1 e to the 2. And putting x equals 0, we get 1/2 times 0 times e to the 0. That term is obviously 0. And then we've got the second expression evaluated between 0 and 1. This is minus 1/4. When x equals 1, we get e squared. When x equals 0, we get 1/4 e to the 0, which is 1/4. And putting everything together, we've got 1/2 e squared, 0 here, minus 1/4 e squared, minus 1/4, so plus 1/4. So overall, we've got 1/4 e squared plus 1/4, okay, which is an answer to that one. And that's more or less similar to most of the examples that appear in the second calculus problem of the current homework. So hopefully those will make sense. And then the third one is this trigonometric integration problem. So we've got a sine squared term and we've got a cosine term. And this is an example where, we know that sine and cosine are essentially derivatives of each other, apart from some negative signs to turn up, but we can deal with those. And so if you've got some integration problem that involves a product of sines and cosines, it's typically a very good idea to let u be one of either sine x or cosine x, because the derivative of u then is the other one. And in particular, if you've got a term, either sine or cosine, that appears only once in an expression like this, a good strategy is to write u to be the other one, sine of x. And the reason for that is, if we write u equals sine of x here, then du dx would be cosine x. So du would be cosine x dx, and the cosine x dx part will get absorbed into du. The sine squared x part we can just write as a power of u. Okay, so if we had something else here besides cosine x, for example, if you had cosine x cubed, in that case, the same strategy would apply, bearing in mind that any even powers of cosine x, like cosine squared x, we can write as 1 minus sine squared. So if you had an odd power of cosine x here other than just cosine x itself, you could write it as like a power of 1 minus sine squared x times a single cosine x, and then do the substitution, u equals sine x. This particular example, please go ahead and write u equals sine x, then du dx is cosine x, and so du is cosine x dx, which takes care of that cosine x dx part and will leave us with just a power of u to integrate. Add the limits. When u equals, or when x rather equals pi over 2, that's the lower limit, then u is sine of pi over 2, which is the y coordinate at the point 0, 1, so it's 1. And when x is pi, then u is sine of pi, which is the y coordinate of the point in the extreme left of the unit circle, which is minus 1, 0. So the y coordinate there is 0. Okay, so our limits of integration, when we rewrite them in terms of u, become, the lower limit becomes 1, the upper limit becomes 0, our sine squared x becomes u squared, our cosine x dx is du, and our problem is just to integrate u squared from 1 to 0, so we get u cubed over 3, upper limit 0, lower limit 1. The fact that the limits here are not in the order that we are used to expecting doesn't matter, we just still plug in the upper limit first, which is 0, and subtract from that the value at the lower limit. So we get 0 cubed minus 3. We get 0 cubed over 3 minus 1 cubed over 3. So 0 minus 1 over 3, which is minus 1/3. Okay, so hopefully those examples are of some help in practicing these general integration problems. If not, or if you have any questions, or if anything here doesn't make sense, just please feel free to get in touch with me anytime, and by email, and we can I can respond by email, or we can make an arrangement to chat about it. Okay, thanks everybody. See you later in the week.